So we saw snapshots of ITCZ for July and January. This animation, which uses various kinds of data, is a good thing to go through. This is actually called ERA interim, so it's the European Union's ECMWF reanalysis. Reanalysis is a term that's used when we take past data which is not distributed uniformly in space and time, so there are data gaps, and then you take a model which we will discuss in the next chapter, is something that integrates the equations that govern energy balance, momentum, thermodynamics, and so on, and we blend them with approaches called data assimilation. What we get is kind of dynamically interpolated past data which has filled the gaps in space and time, so it gives us a way to look at processes. There are lots of details, there are lots of issues which matter, but for our purpose it's not very serious. It's incredibly useful information for doing large number of studies. So we are looking here at precipitation in centimeter water equivalent, so snow also is converted hail. Every kind of precipitation is converted into water for this purpose, and this reinforces kind of what we saw with some additional information. So it's going through the yearly cycle averaged over 1979 to 2000, and let's say here we are in August. Sun is to the north, ITCZ is clearly to the north, and we will come back to the Indian Ocean sector, but we are already in the winter months. So here we have the rainfall that is moving back and forth, as we said. Some places it's very obvious. For example, here over Africa and South America, you can clearly see the seasonal migrations. So here it is boreal summer, June, July, August, almost disappearing, or lower part of the rainy season, and during the boreal winter months, massive amounts of rain here. The same thing happens here over Africa, the migrations over the annual cycle. And of course we said the ITCZ here remains to the north because of various asymmetries, and we didn't mention so much the component here and a tiny bit of a component here. This is called the South Pacific Convergence Zone. So ITCZ is what we refer to as the northern part of it, but when the ITCZ moves to the south, the ITCZ that remains to the north splits into this southern part, which is called the South Pacific Convergence Zone, and it's not as zonally or longitudinally situated as the ITCZ. It's got a tilt, and there are some details here that I won't get into. So you can see that during the winter months, boreal winter months, ITCZ, the SPCZ, South Pacific Convergence Zone, gets strong and extends southeastward, and there's a similar feature here called the South Atlantic Convergence Zone. And then you have the polar front here, or the subpolar front here in the Southern Ocean, which we said is different than what happens here. So here we have the clearly defined storm track, which also waxes and wanes. So you can see this here. We will learn the relation to the ocean features later in this chapter. So you can see the storm track here and the storm track there, which get stronger during the winter season. So boreal winter, northern hemisphere winter season, the storm track gets very strong. You can relate it to the energy transport here, because the energy transport is related to the equator to pole energy gradient and the temperature gradient. When you have the boreal winter, you have the coldest temperature at polar latitudes, so the equator to pole temperature gradient is the strongest of the year. So that also relates to how much energy has to be moved in the winter, and how that leads to a stronger storm track, stronger convergence at the meeting of the Ferrel cell and the polar cell, as we said before. But there are other dynamic details like the baroclinic instability, angular momentum conservation issues that we mentioned as well. Okay, so large parts of these latitudes it'll be snow, not rain, but it doesn't matter. On the ocean you get these storm tracks, and the Indian Ocean also needs some special attention, especially if we look at the boreal fall winter months. The ITCZ is to the south, sun is to the south, so clearly defined ITCZ. As sun moves north, ITCZ wants to move north, it does here, but here it splits. The ocean is warm, so the ITCZ remains, but in the next loop again we will see that there is a lot of activity in the east, and then the southwest monsoon that we talked about gets established. So you get a lot of rain on the Bay of Bengal, Western Ghats, orographic rain, Himalayan foothills, orographic rain. Orographic rain is where winds are forced to climb over the mountains. During that time they expand, condense, and dump a lot of rain on the windward side. On the leeward side, either there is no rain or much less rain because the water vapor has been squeezed out on the windward side. The core monsoon zone, so-called central Indian core monsoon zone, gets rain during the summer months as well, as you can see here. So there are meters and meters of rain falling at the mountains here and here. One of the highest rainfall regions is here, which gets I don't know, more than 10 meters of rain if I remember correctly, but please check. Burmese mountains. Bay of Bengal is warm, so it gets a lot of rain as well. And of course there are also monsoons over the Asian region, Australian region, Africa, West African monsoon, East African monsoon. There is also something called the North American monsoon. So monsoon is a general word now being expanded. Original word comes from Persian, which means season, mausham, I don't know, something like that. So because a monsoon has such a strong seasonality, they had figured out that in the summer it's easier to go east using the southwesterly winds, and to come back it's better to wait for the winter and use the northeasterly winds. So they call them the seasons or the monsoon. But now any region which has a significant rain difference between the summer and winter is called a monsoon. So West Africa has a monsoon, East Africa has monsoon, which actually happens twice a year. North America has a monsoon by these definitions. There is a South American monsoon as well. So there are relations between the African, Indian and Australian, Asian monsoons here, which we won't get into, but you can see wherever there are warm waters that we saw before, there is a lot of rainfall. And there is also a Mayu-Bayou front or East Asian rainfall monsoon season, which is the extratropical rainfall because it's not within the tropics where most of the monsoons happens. So all these are kind of seasonality of the rainfall, and most of these white regions, especially over the subtropical high, are the evaporative regions. So if you look at evaporation minus precipitation, it will be negative here where precipitation is much larger than evaporation, but these are regions where E minus P is positive because there is much more evaporation than precipitation. So these regions are evaporating and supplying moisture to the ITCZ in that Hadley cell that we saw. And the moisture supply here is different processes because of the baroclinic instabilities and forced rising of air and the storm tracks and so on and so forth. Okay, as we said, Southern Ocean is different because it's a channel and it creates different ocean circulation, atmospheric circulation and combined circulation as well. So for the Indian monsoon crowd, this is very important, how the ITCZ splits and the rainfall gets set over land as well as over the ocean, as opposed to other places where the ITCZ is just moving north and south. Okay, I cannot think about anything else. There are lots of other things, winter precipitation, summer precipitation, and so on, that one could talk about, but I think I captured most of the dominant features of rainfall distribution around the globe and its seasonality. Under global warming, the questions are: how is the rainfall distribution changing? Whether the ITCZ is getting thinner or thicker, whether evaporative regions are becoming more evaporative, rainfall regions are becoming more rainy, and how the rainfall changes. So rainfall often is thought in terms of its duration, how long it rains, its intensity, how heavily it rains, and its frequency, how often it rains. So we will see later on when we look at climate impacts that global warming, which is the warming of the atmosphere, which we said increases its capacity to hold water, is also getting more energy because the water in the atmosphere can condense, and the increase in water vapor is directly related to the warming through the Clausius-Clapeyron equation that we talked about. So 1 degree warming will give you 7% increase in water vapor on average. But does it mean rainfall will also increase 7%? No, it turns out that the average rainfall only increases 2 to 3%, but the rainfall distribution changes. So the rainfall will come as heavy spells or extreme events. So if there is a monsoon over India between June and September, for example, the number of rainy days, instead of being 100 and something, may get squeezed into 50 something, so that rainfall is maybe falling less in total amount over the season, but it's falling in very heavy spells. This has obviously disastrous consequences in terms of crop damage, flooding, and so on. Plus, when it is raining heavily in some place, it is raining less in other place because the moisture is being extracted by the heavy rain. So you also combine droughts along with these floods. So it creates all kinds of problems. So we will discuss a little bit about extreme events in the later chapter, where we look at climate impacts, which we mean climate change impacts. So in this book that I'm covering by Schmittner, we will do climate science and climate change and a little bit about impacts in climate policy and solutions, but I will take another book completely focused on climate change and add some more points, some overlap, but it's okay. And then we will also cover some modeling in this book, but I'll also take another separate book which is focused entirely on modeling and cover some more about modeling. Some overlap is again okay. It re-emphasizes the concepts. Okay, so this is the distribution of rainfall for now.